Hello students, happy morning. Unit 3 Magnetism and Magnetic Effect of Electric Current continuation video. In our previous class we learned about solenoid. We know very well solenoid is a long coil of wire that is wounded in the form of helix known as solenoid. This one is a solenoid. If suppose we apply a current in the solenoid, then it behave like a magnet. The magnetic field inside the solenoid is uniform, that is parallel to the axis of the solenoid. Okay, that you know very well. Using right hand palm rule, we can identify the north and south pole of the solenoid. Okay, here we see what is toroid. Toroid is another form of solenoid. Here it can be made from solenoid only. A solenoid is bent in such a way its ends are jointed together to form a closed ring shape called toroid. Okay, if suppose it is a solenoid, the solenoid ends are jointed together and form a closed ring shape, that is known as toroid. Okay, this one is a toroid. Then the magnetic field is constant inside the toroid. Okay, inside the toroid the magnetic field is always constant. But the magnetic field interior and exterior region is zero. Magnetic field at interior and exterior region of the toroid will be zero. Let me see how the magnetic field in exterior, interior and inside the toroid. Okay, here I consider a toroid. The dot represent the current going into the paper. Okay, here the cross represent current coming out of the paper. Okay, let me see. I consider a interior region, open space interior region to the toroid. We will see the magnetic field at that interior region. Okay, so I consider a point in the interior region. Okay, then I construct a ampere loop in the form of circle of radius R1. Okay, this is named as loop 1. Okay, then the length of the loop is loop 1, that is equal to, how to calculate the length of the circle? By cutting at any point, then measure the length, then we will get the circumference of the circle, that is 2 pi r1. Okay, then we can apply Ampere circular law for that Ampere loop, Ampere's circular law. That is closed law, that is loop 1 B P vector dot dl vector, because we need magnetic field at the point P. Okay, that is equal to mu naught I enclosed. I enclosed is a current enclosed in a loop 1. Okay, here we know very well I enclosed is 0 because there is no current in the loop 1. Okay, so we can write this equation as closed law of loop 1 BP vector dl vector is equal to 0. Okay, this equation will gives the idea about the magnetic field at the point P is 0. Okay, we can write BP vector is equal to 0, so there is no magnetic field because it does not encloses the Ampere loop does not enclose any current. Okay, here let me see the magnetic field in exterior region of the toroid. Okay, so I consider a point Q in the exterior region. Then I draw an Ampere loop around the point Q. Okay, in order to find the magnetic field at the point Q, that's why I draw an Ampere loop. Okay, the radius of that loop is R3. Then the loop is said to be loop 3. Okay, here let me see the magnetic field in that exterior loop. Okay, we know the length of the loop is given by the circumference of the loop 3. Okay, length of the loop can be written as length of the loop 3 is equal to 2 pi, that radius is r3. Okay, then we can apply Ampere's second law. That is closed interval of loop 3 b vector at q dl vector is equal to mu naught I enclosed. Okay, here the current enclosed in that Amperian loop is equal to 0 because current coming out of the plane of the paper is cancelled by current going into the plane of the paper. Okay, see this dot cancelled the cross. Okay, that means the current going into the paper is cancelled by the current coming out of the paper. Okay, let me see the current coming out of the paper is cancelled by current going into the paper. So the current in that Ampere loop will be 0. So we can write closed interval of loop 3 b q vector dot dl vector is equal to 0. This will be 0, only the magnetic field at q will be 0. Okay, then we can write bq vector will be 0. Then let me see the magnetic field inside the toroid. Okay, we know very well inside the toroid the magnetic field is constant and it is parallel to the direction of that toroid. Okay, let me see. Here I consider a point inside the toroid. Okay, suppose I consider here that is named as S. Okay, then I draw a Amperian loop, that is circular Amperian loop of radius R2. Okay, this loop is named as loop 2. Okay, then the length of the loop is loop 2 is 2 pi R2. Here we will apply Ampere's second law, Ampere's circuit law, that is closed interval of loop 2 bs vector dot dl vector is equal to mu naught I enclosed. Okay, here I enclosed is a current enclosed in a loop. Listen, here it is a loop. Inside the loop there is a current. In that solenoid the current flowing through the loop is I. Okay, so it having n number of turns, so we can write I enclosed as I enclosed is equal to number of turns into current in each loop. Okay, then I enclosed we get this value. Then this is a dot product of two vectors. This can be written as closed interval of loop 2 bs vector bs dot dl bs vector dot dl vector is equal to closed interval of loop 2 bs dl cos theta. Theta is an angle between b vector and dl vector. See, here I consider a length element dl. Okay, the magnetic field also in this direction only. The angle between they are parallel to each other. Then the angle between dl vector and b vector will be 0. Okay, so cos theta became 0. Cos 0 degree became 1. Okay, then we can write closed interval of bs dl, that is equal to, then the magnetic field is uniform inside the loop, so we can take outside the integral, that is loop 2, then integral of loop 2 dl, integrating dl we get entire length of the loop, that is 2 pi r2. Okay, then we get bs 2 pi r2. Then equate this value with this value. Okay, we found this value. Then we know mu naught I enclosed became Ni. Okay, we know this value is bs 2 pi r2. Then this value is mu naught I enclosed became N into I, Ni. We need the magnetic field inside the toroid, that is bs is equal to mu naught Ni by 2 pi r2. Here it is the length of the loop, then it can be written as number of turns per unit length. Okay, then N is equal to N by 2 pi r2. It is a number of turns per unit length. Then magnetic field inside the toroid bs is equal to mu naught N I. Okay, here in the toroid the magnetic field inside the toroid won't be there, then the magnetic field in the exterior and interior region will be 0. Okay.